Hello again. So we've looked at the Brymen BM839. Again, this was an automotive meter, and we also did some life cycle testing on this BM860. But when the box first arrived, remember I said that it looked awfully large for just 2 meters. So let's have a look. Yep, there's a 3rd meter. So this is the Brymen 830 series, and we can see this is the BM839. Some of the basic features of the meter are its 20,000 count, as a 61 segment analog bar graph that updates 60 times per second, so that's quite fast. Looks like it has a dual display, but it looks like it might be limited to only displaying frequency. The best DC voltage accuracy, it looks like, is 0.045%. The AC bandwidth for this meter is 20 kilohertz. When you're using the continuity mode, it enables the backlight as well as the beeper. That's kind of a nice feature. Transient protection up to 8 kV with a 1.2 microsecond rise time, 50 microsecond, and that would be the full width half height. Lightning surge. There's the low voltage directive, meets 61010, but notice beneath that EMC EN 61326-1 2013 standard. So I'm going to go out on a limb and say that this meter is probably going to be quite robust. Let's go ahead and take it out of the box and we'll have a look. It comes with a 23-page manual. Comes with the standard Brymen leads and a small thermocouple. You can see it's labeled 1000 volt Cat 3, 600 volt Cat 4. Looks to be the same size as the BM839. As you can see, the two cases are basically identical. I can see one difference right now. Notice that the microamp and amp jacks have been swapped from the BM869. It looks like it can't compute the AC plus DC values. Let's just see if it turns on. One of the things Brymen had told me is that they had improved the LCD on the BM839 over what the BM869 had. So let's just take a look at the two side by side. Sorry about the glare. Well, the viewing angle on both meters does not look that bad. Let's just swap their position. I'd say the BM839 does have a little bit better contrast than the BM869. The other advantage to the BM839 is the cost. I was not able to find a distributor for this meter where I could get pricing, but Brymen told me that this meter is about 80% of the cost of the BM869. I was curious because I knew that this meter had a peak detect. This is looking at the Brymen BM869 manual. You'll notice they call it a 1 millisecond crest capture mode. And this is looking at the 839 manual, and you'll notice it's now a 5 millisecond crest capture. I wonder how this is tied in with the overall bandwidth of the meter. That could be the limiting factor. I think before we do anything else with the meter, let's go ahead and just do a real basic functional test. We'll start by applying a DC voltage. It should read 0. Next, this will be a 0 to 5 volt square wave that's AC coupled, and this is at 60 Hertz. So we are displaying roughly 2.5 at 60 Hertz. That's correct. This is no longer AC coupled, so it's switching between 0 and 5 volts, and you can see the meter's not having any troubles reading frequency or voltage. This would be at 30 Hertz. That's correct. This is 15 Hertz. That's correct. And this will be 120. That is correct. This will give us roughly 70 volts AC, and the frequency is roughly 3 kilohertz. That's correct. This will give us roughly 115 millivolts. That is correct as well. You can see it cannot display the frequency. This would be at 60 hertz. Let's just try it real quick in the millivolt range. And there you have it. So 60 hertz at 118.6 millivolts. So let's try DC volts, and this will be 5.0. You can see that is correct. Again, this is AC coupled, so it should read 0. This is DC coupled, so it should read 2.5 volts. Again, this meter does not support AC plus DC like the Brymen BM839S. And personally, that's a feature that I like having. Let's just change over to resistance. And we'll start by shorting the leads. You can see it's reading 0 ohms. Let's try it with a 0.1. Let's see, it reads 0. Let's try it with a 0.5. Looks like 0.4. This will be a 1 ohm. And a 50 ohm. 100 ohms. You can see the meter is quite quick. So 1K, 10K, 100K. This will be 1 meg. This will be 10 megs. This will be 40 megs. Let's try 100. I don't think it can read this. The meter does have conductance mode though, so we just press select. And this should give us 10 nanosiemens for 100 meg. That's correct. Let's try it with a giga ohm. This should be 1 nanosiemens. And that is correct. Now, of course, the meter is 20,000 counts. And the way you know that you've selected that is, it looks like on the bar graph there is a 6 in the lower right corner. And when I select 20,000 counts, see how it changes the resolution of the bar graph, and we see the 20 displayed now. So now, with a higher resolution, you can see we gain a digit, so this would be 100 ohms. Again, 10K ohms. Now the meter has a special mode for looking at lower resistances. So the way to get into that special mode is you select the range. You notice the meter displays short. Once the meter beeps, it's now compensated for the leads. So it's a little bit better. There you go, 1.0 or 0.99. So a little bit of an improvement. Let's try it with 0.5 ohms. And again, let's just reset it. Again, this will be with the 0.5 ohm resistor. So it's definitely made some improvement, but you're probably not going to use a meter like this to read these low values anyway. All right, so let's try capacitance mode, and this is with an open. This will be 150 picofarads. And 1 nanofarad. And a 0.1 microfarad. Looks pretty good. And this will be 1 microfarads, 10 microfarads, and this will be 100 microfarads. And here's a single diode, 2 diodes. Let's try it with our white LED. Again, this should drop roughly 2.5 volts, and you can see it does that just fine. Let's try continuity mode. It's kind of a nice feature having the backlight flash. Let's just try temperature. Again, this should be 500 degrees Celsius. And this should be roughly room temperature and a little over 1,000 degrees. So it's got quite a good range. Again, our box can't supply a whole lot of current. This will be 100 microamps. And this will be 10 microamps. Let's just switch over to the microamp range. There you go, 10 microamps. And this will be 1 microamp and 100 nanoamps. So that all appears to be fine. On the far left, we have the Unity UT181A. To the right of it is the Gaussian Metrowatt MetroHit Ultra. Then the TPI 194.2. Of course, the Brymen BM839S. And then on the far right, we have the SEM DT9939. The Unity 181A costs roughly $300. This is a Cat 4 600 volt rated meter. It has a resolution of 60,000 counts. It has 2 temperature probes. It can also measure conductance. This particular one has been modified. It was damaged after a single ESD event. The changes that I've made to this meter only really affect its performance as far as the robustness of the meter. The Gossen M248B costs $850. It's Cat 4 300 volt rated and has a resolution of 300,000 counts. Again, this meter has been modified. What I've done is I've fabricated a shield for this, but that's the only change that I've made to this meter. The TPI meter is actually produced by a company called Summit. This meter costs $250 and is Cat 4 600 volt rated. It's a 50,000 count meter. Of course, then we have the Brymen BM839S. Again, still my favorite meter out of all the ones you see here. This meter cost me $230. It's Cat 4 1000 volt rated. This is a 50,000 count meter, but it does have a high resolution mode of 500,000 counts. This meter, like the Unity 181A, also has 2 thermocouple inputs. This particular SEM meter I bought from Ruby Electronics. They were running a sale when I picked this up, and I got it for $120. A few other people picked up that deal as well. This meter is Cat 4 600 volt rated. It's a 40,000 count meter. All the meters that I'm showing except the BM839 are capable of reading the AC plus DC. Of course, all these meters are true RMS. The reason that I chose these 5 particular meters is they are currently all in production, and they're also the highest resolution meters I have. Again, a friend of mine had given me this Fluke 189. This would be a nice meter for this comparison. Unfortunately, you can't purchase this meter brand new anymore. And I'm sure a few of you are asking, well, where's the UT61E? Again, this meter has been highly modified, so I'm not sure if this would be a real good comparison. Maybe we'll use it later on in the video. Of course, the adaptive backlight still works. Where I've ran comparisons where we've looked at the DC currents, I'm not aware that I've ever looked at the performance of the AC current inputs of the different meters. So in order to generate that AC current, I have a power amplifier. This is just a homemade amplifier. It's good for low frequency work. What I'm going to do is just drive this thing off of our ARB. And what I'm going to do is use this UT210E. And you can see I have an analog output. And I'm just going to connect this right to our oscilloscope. Now again, I should mention this UT210E has been highly modified. This meter has a bandwidth now of roughly 100 kilohertz. So I thought I'd give you a little demonstration of that higher bandwidth. So here you can see I have my iPod out, and this is attached to our power amplifier. The output of the power amplifier is driving the input to all the meters, which are in series. And again, here I have our current probe. And then the output of this current probe just connects to these powered speakers. They're not a very good set. So we'll just clamp this around one of the cables. Let's go ahead and we'll turn on the iPod. Change the polarity. So that's what a few hours of engineering time modifying one of these probes will get you. You can see on the left I've gone ahead and added my highly modified UT61E. Again, to be clear, even the 10 amp shunt on this has been modified. So the UT61E is reading 564 milliamps, 555, 564, 567, 565, 564, and 562. You can see this is with a pure sine wave. And also you can see the frequency, it's 50 hertz, 50, and 50 over here on the metrowatt as well. Let's just go ahead and increase the current a little bit. Alright, you can see I've changed it over to a square wave. And again, you couldn't do that with this probe not being modified. I've also increased the amplitude slightly. This is with, again, a 50 hertz sine wave. It has a 20% AM modulation on the 10th harmonic, and the shape of that modulation waveform you can see is sinusoidal as well. Again, the scope you can see I have a square wave, again, that's AM modulated. Right, let's just zoom in a little bit. You can see I have a sine wave that's been clipped, and you can see we are also running at 400 hertz. It's a pretty nasty waveform here. You can see this is again the clip sine wave, but now I have a 20% AM modulation using a triangle wave off the 10th harmonic. It definitely has a triangular shape as far as the modulation. This is one of the standard IEC waveforms, and you can see I've gone ahead and increased the amplitude as well. And I've also changed the frequency. You can see that this is now running at 2 kilohertz. There's certainly no problems with the BM839 looking at AC currents. So again, all 7 meters are in series and they're connected to my DC bench power supply. These are all set to their DC current modes. And you can see the UT61E is displaying 0.213, 0.215, 0.214849, 0.2153, 0.2145, 0.2145, and 0.214. Currently all the meters are set for their milliamp range, and I'm applying almost 190 milliamps. Also have our fluke meter out. And what I'm going to do is measure the burden voltage of each of these meters. Roughly 670 millivolts. I expect that's the highest one. 690 millivolts on our 181. Our Gaussian is about 112. Our TPI is about 275. The BM839 is 471. The BM839S is 328, and our little SEM meter is 1.21 volts. So it looks like our SEM meter is by far the worst of the group. And I've changed all the meters to their microamp range, and you can see we're outputting roughly 650 microamps. Let's see, the UT61E's burden voltage is now, let's call it 8 millivolts. The UT181A is 36 millivolts. The Gaussian metrowatt is 38.3 millivolts. Looks like our TPI 194.2 is 74.4 millivolts. The Brymen BM839 is 75.37 millivolts. Looks like our BM869S is 75.5 millivolts. And our SEM meter is 373 millivolts or so. So I don't see any problems as far as the BM839 being able to read DC current as well. It looks like all the meters are reading roughly the same value. Alright, so currently all 7 meters are attached in parallel. These are connected to my Fluke reference standard. You can see we're putting out 10 volts right now. This is with the standard set to 1 volt. And this is with the Fluke standard set for 1 millivolt. Looks like the battery in our TPI meter is completely dead now. This might have been the original battery that was with the meter. You can see I scrapped so many meters. I have this continuous supply of cheap batteries. There we go. So currently I'm at 1 volt, and again we're at 60 hertz. And what I'm going to do now is just increase the frequency, and let's see what the 3 dB point is for all these meters. Alright, you can see we are currently at 11.8 kilohertz, and we can see the SEM meter is pretty much dead on at 0.707. You can see the UT61E is starting to peak up. It's reading 1.0276, it looks like. Let's go ahead and continue increasing the frequency. Alright, this is currently at 46 kilohertz, and we can see the modified UT61 is now at its 3 dB point at 0.709. Again, this meter has been highly modified on the front end. I think if you went back and look at the videos that I made where I was modifying the UT61E, that you would find that the meter had a very respectable frequency response. But I think that that helped contribute to the reason that the meter failed the ESD testing. You can see we're at 200 kilohertz. Notice that the BM839 is now really peaking up. It's 1.2393 volts. Again, the BM869S is reading 1.015. Of course, our SEM meter now is pretty much dead. The TPI 194 is reading 1.0884 and 1.0332 for the Gaussian. And our UT181 is reading 0.9867. Let's just see if this continues to peak up. Notice that the Gaussian Metrowatt is having problems trying to read this, but this seems to be about the peak for the BM839. You can see we're at roughly 400 kilohertz. And you can also see the BM869S is down to about 0.8 volts. So it's getting near its 3 dB point. Looks like the UT181A is 0.97. Of course, our UT61E is reading 0 volts along with our SEM meter. Again, this is way outside of the range that any of these meters are rated for. I think what I'm going to do is just disconnect all the meters except this BM839. And let's just see where the frequency counter stops working. It looks like this is roughly the upper end of it, so about 6 megahertz. Looking in the manual, I don't see where they specify what the top end is for the frequency counter. They basically just talk about the AC. You can see it's rated for up to 20 kilohertz. This meter basically works like the rest of the Brymens. You press the select key, then turn on the meter, and then that'll disable the auto power down. Currently I'm applying a 50 hertz square wave to all the meters, and again you can see they all basically read the same thing. The UT61E is a little high at 10.098. Looks like 050, 061, 070, 074, 069, and 072. But it looks like they're all reasonably close. Alright, let's have a look at the bar graph update rates. This is looking at the BM839. You can see how smooth this is. Compare that with the TPI 194. You can see with this meter, they basically update the bar graph at the same rate as the normal display. And you can see the same thing going on with the SEM meter. This is one of the nice features with the UT181A. You can see they center the bar graph around 0, and then it displays both positive and negative numbers. Again, this is looking at the manual for the BM839, and we can see it's a 61 segment bar graph that updates 40 times per second. So it's a little slower than these two meters. I think these are both at 60. As a 61 segment analog bar graph that updates 60 times per second. Let's go ahead and increase the frequency. This is at 1 hertz, and again this is a sine wave. This is with 4 hertz being applied. And now you can start to see the problem with the meter. See how it just kind of jumps around. See how smooth these meters are. You actually get some indication of what that waveform is doing. If you're trying to align a piece of equipment, say with a potentiometer, and then you're looking for the visual feedback, these work out quite well for that. So I spent a little bit of time with the BM839 to see if it was sensitive to RF in any range between about 400 kilohertz and about 1.3 gig. And again, that's just basically using an antenna and waving it around the meter. And then I also inject directly into the front end of the meter. I also did some measurements for the continuity tester. This meter has a short circuit current of 184.4 microamps. It has an open circuit voltage of 1.656 volts. The resistance where it detects a short is 110 ohms. Where it goes open again is 224 ohms. Using a 50% duty cycle waveform, at the point where the meter will start to skip a beat is about 7.6 hertz, and the minimum pulse width that it could detect is about 30 milliseconds. Right to my left, you can see I have the high voltage power supply out, and currently it's attached to my BM869S on the right and the BM839 on the left. I'm going to start by applying a DC voltage. See, the two meters read very close. And this is the upper limit of my power supply. See, both meters basically reading the same value. I've restrapped our power supply. It's now putting out a square wave. You can see the amplitude is roughly 544.3 volts. And you see the same thing in the upper right on the Brymen BM839S. It's 539. The interesting thing is, notice this is displaying 200 hertz. Let's just change this over to the AC volts, and you can see it's 100 hertz. This is actually correct. It is a 100 hertz waveform. So I'm not understanding why this is having troubles with this. So let's try changing the DC bias, and you'll be able to monitor that on the BM869S. And let's see if that affects the AC measurement. You can see this is roughly 300 volts of bias, and that's having no effect. Let's just try going negative with it. And again, you can see no effect. I don't understand why it's having trouble reading the frequency though. So let's just change the frequency a little bit and see if that has any effect. And you can see we're down at 50 hertz now, and the meter's reading 100. So just for a comparison, you can see I brought out my DT9939, and you can see it basically matches the BM869S. They're both displaying 59.99 hertz. That is correct. And again, I'll just turn off the power, and we'll plug it back into the BM839. And again, you can see double the frequency, 120 hertz. So yeah, I'm not sure what's going on with it. I don't see this problem at lower voltages. So other than reading 2 times the normal frequency, I don't see any other issues as far as reading high voltage AC. Again, this is looking at the BM839 manual. You can see the operating temperature is minus 10 degrees C to 50. When we look at the BM869 manual, again, we can see the operating temperature is 0 degrees to 45. Of course, the BM869S can run over a wider temperature range. I'm not sure if this is because the meter is less accurate. You know, if they open up the windows on the 869S, you know, could they rate it for a wider temperature range? Yeah, I'm not sure. You may remember this. It's my meat packing box. Notice I finished lining the box. And you can see I got the meter inside. Currently have it connected to our Fluke standard. You can see we're putting out roughly 10 volts. Go ahead and close this off. So we've started up the software, and we're going to start it by cooling. We'll just set it to minus 10. We'll see how cold we can get. So we've already dropped 2 degrees. It's going down fairly quickly. We'll let it set for a half an hour or so and we'll come back to it, see how it's doing. You can see I have both windows open in the lab, trying to cool down the room. And you can see it's winter here. We had a bit of a warm spell and lost some of our snow. Basically, I'm trying to cool down this meter to -10. Right, you can see we started off at 24 degrees C. I had forgot to turn off the auto power down mode of the meter. So when I checked it, of course the meter was turned off. So I'd open up the box and then shut her back up and worked our way down. We got down to about 0 degrees C and you can see we started losing some steam. So what I did is open up the windows in the office here, and you can see we're slowly working our way down to -10 degrees now. Let's just go ahead and turn on the camera, and you can see it's 9.988 volts right now. Meter seems to still be working just fine. Right, so you can see we're a little past -10 degrees Celsius now. Let's go ahead and we'll have a look at the camera. This is the coldest I've had this box with a meter and the camera inside. Alright, let's go ahead and we'll heat the meter up. First thing we're doing is closing the windows for the office. Change our set point to 50 degrees Celsius. And here you can see it's already changing. Right, you can see we've been up at 50 degrees Celsius now for about 30 minutes. We'll go ahead and enable the backlight. Alright, so it looks like 10.013 volts. So almost a 20 millivolt shift. Again, I would have liked to have held this thing at, -10 for a longer time, but the room was getting pretty cold up here. But all in all, I'd say the meter definitely works over the operating range that they claim. Alright, I think it's time we have a look inside the meter. Let's just compare this with the BM839. Again, you can see the rubber boot for the two is identical. Of course, the BM839S has an access door here for the battery. You also notice that it has the interface for the serial port. Looks like just the 2 screws hold this in. It was shipped with ever-ready Energizer batteries. This is a little different than the BM869S. So you actually have access to the fuses without removing that back cover. Of course, they have the standard FF400 SIBA fuse. And again, the Busman fuse for the higher current. Looking at the battery holder, these appear to be gold plated. I don't think I've ever seen a battery holder like that. Again, like the BM869S, they've gone with the mezzanine board. Switch is similar again. It looks like it has contacts on both the top and bottom side. Notice the shielding. You can see the high voltage resistor down there. I think, like on the BM869S, I think this is only held together with this one screw. It's pretty tight. I don't think that's ever been out of there before. Just see. Oh yeah, it's going to come right out of here. Again, a very similar switch design to the Brymen BM839S. Guess I would expect that. You'll notice one thing. There is no gasketing like the BM869S. But you'll notice that the input connectors do have the rubber O-rings. Getting some additional shielding. Looks like a few adjustments. It's quite a bit different than the BM839S, but let's have a look at the input stages. Notice your high voltage resistors here, and it looks like there's at least two mobs. You can see the one here and here. I suspect that the black sheathing here and here are covering up the PTCs. I'd like to pull this thing apart, but I plan on life cycling the switch on this meter, and I'd really rather minimize the amount of times I have this thing apart before I run that test. So it'll have to come apart in order to run that, because I'll have to pick which contacts I'm going to use, and I want to know if it's lubricated or not. So I think while we have this thing apart, what I'd like to do is we'll go ahead and pull the fuses, and we'll run some high voltage into the current inputs, and let's see if there's any problems with this thing breaking down. You can see I have our ESD gun out, and again, this ESD gun can supply DC voltage as well. This meter is rated for 1000 volts. We'll go ahead and start with the amps jack. And again, the standards call for 1.5 times the operating voltage, so basically 1.5 kV. And it should be able to hold that without breaking down for at least a minute. So let's just have a look. So there's 1.5 kV, and we'll just let it sit. Let's go ahead and take it up to 2 kV. Let's try 2.5. It's 3000 volts. This is 2 times what the standard would call for. Alright, let's try the same thing with the milliamp input. And we'll just start off at 1500 volts. Alright, that's roughly a minute. Let's go ahead and continue up to 2000 volts. Let's try it at 25. Up right there. Again, this is 1000 volts higher than what the standard calls for. And we can see the milliamp function works just fine. Let's try it in the microamp range. Again, that looks to be fine. And let's go ahead and test the amps input. This should beep. Actually, if we go this way, it should beep as well. So again, on the amps range, put roughly 900 milliamps through it, and it seems to be just fine. So it looks like the meter handles that test just fine. Alright, you can see I have the meter attached to our transient generator. Again, I'm just going to be applying a fully rectified 220 volt signal into the meter. And again, the transient generator will limit this to about 40 milliamps before I'll shut it down. That's where I have it programmed at right now. So if the meter does start to draw excessive current, at least the transient generator will disable its output. That should minimize the damage to the meter. So you can see it's reading 120 volts, and that's in the AC mode. And because it's fully rectified, you can see we're at 120 hertz. DC, this should read 240, and that's correct. So what I'm going to do is rotate the knob through the various functions. Of course, I don't test the current inputs, but then we'll go back and functional test the meter and see if we've caused any damage to it. just see if it still reads voltage fine. Yep. Alright, let me go ahead and check it. Alright, so the meter passed the functional test just fine. You can see I have my ESD gun out again. Again, this gun basically follows the IEC standard. It puts out about a 15 amp peak pulse in under 1 nanosecond. Again, I'm going to be applying 5 transients, both positive and negative, and I'll go through each mode of the meter, and then we'll go back and functional test it. Oh. Did we kill it? It definitely reset. You see that? It actually hung it. Let's just try that again. Took it that time. Alright, let me go ahead and have a look. Let's see if we caused any damage to the meter. I think the first thing I want to know is, does the temperature input work? So again, this should be about 500 degrees Celsius, and that appears to be just fine. Let's go ahead and turn it down. Again, this should be room temp and a little over 1,000 degrees. So it looks like no problems there. Let's just see if the millivolt input was damaged. Again, this should be about 118 millivolts or so. And you can see it's at 60 hertz, so it doesn't appear that we damaged that part of the meter. Let me go through and I'll finish functional testing it. The meter passed functional testing just fine. You can see I now have it attached to our transient generator again. And we have our high voltage probe out, and currently that's attached to our Fluke 97. Again, sorry about the glare. You can see the scope is set for 1 volt per division. That's basically 1,000 volts per division, and it's also 200 microseconds per division. So you can see it's 1 division up or 1 kV. So this is where we're going to start. So 1,000 volts peak with a 100 microsecond full width half height. Again, this transient generator will put out about 20 joules tops, and that's if the meter broke down. And this is using a 2 ohm source impedance. Again, we'll be applying 5 transients, both positive and negative, with each mode of the meter being selected. And then we'll follow that up by functional testing it. And then I'll just increase the voltage until the meter fails, or the meter survives everything I can throw at it with this transient generator. Alright, so the meter passed functional testing just fine. I've gone ahead and changed our transient generator again. So as you can see, the scope is still set for 1,000 volts per division, and we're now 1.5 divisions up, or 1.5 kV. Again, we'll be applying 5 transients, positive and negative, with the meter set to each mode. Clock battery just died. Alright, that's it. We'll go ahead and functional test it. Alright, so the Brymen BM839 survived that test just fine. So looking at our data sheet, I want to go back and check, but yeah, the Fluke 87V, this is actually where it had failed. 1.5 kV, 2 ohm source. It actually took out the front end of that meter. So this is at 1 kV. This is 1.5. You can see there's been quite a few failures at these two levels. This does not include every meter I've ran. This is an older sheet. Anyway, you can see I've reprogrammed our transient generator. Again, it's still 1,000 volts per division. You can see we're now 2 divisions up, or 2,000 volts peak. And again, I'll just repeat this test with 5 transients, positive and negative, with each mode. And that's it. Alright, so the BM839 passed that test just fine. And you can see I've reprogrammed our generator. Still 1000 volts per division, 2.5 divisions up, or roughly 2.5 kV. Again, this will be 5 transients, positive and negative. Alright. Of course, our batteries died in the scope during the middle of this test. So we got to get those back on the charger. We'll go ahead and functional test this meter. Get the pack changed out. And then we'll continue on with our testing, assuming there's no problems with it. The BM839 survived that test just fine. And you can still see we're at 1000 volts per division. We are now 3 divisions up, or 3 kV peak. Alright, that was the end of the 3 kV transient testing. So it looks like the BM839 survived the 3000 volt transient just fine. Now we start incrementing by 1000 volts. And you can see we're still 1000 volts per division. We're 4 divisions up right now, so 4 kV. Again, this is going to be 5 transients, each mode of the meter. I have pretty high confidence that this Brymen is going to survive this test just fine. As a matter of fact, I have pretty high confidence that it will survive everything this transient generator can put out. Okay, that's it. Looks like the BM839 passed that test just fine. Again, we've changed our fluke to 2000 volts per division, and it's 50 microseconds, so you can see we're about 2.5 divisions up, or 5 kV. We're getting close to the limit of what this generator can put out. So again, 5000 volts and 100 microsecond full width half height with a 2 ohm source impedance. 5 transients with each mode of the meter. This is again looking at the waveform. You can see it's 2 volts per division, or 2000 volts, and this is 100 microseconds per division. And you can see we're almost 3 divisions up and about 100 microseconds wide. Okay, I've got our transient generator set up for its maximum output voltage, and this is just shy of 6000 volts. If you watch my previous video, hopefully it's going to be this meter surviving this same transient. Alright, you can see I've changed over to our original transient generator. I'm also going to be using our LaCroix scope. Again, this transient generator could put out a very high voltage pulse, but the energy that it produces is somewhere around 10 joules. It's not a whole lot. So it's currently set for 6000 volts. This is where I typically start at. And I'm going to, again, apply 5 transients, positive and negative. Also, this generator is using a 2 ohm source impedance as well. Again, this generator, if I wasn't clear about it, is putting out a 50 microsecond full width half height instead of the 100 microsecond that this generator puts out. This generator actually is capable of putting out a 100 microsecond full width half height. It's just not strapped for it right now. And you can see we're just a slight amount over 6000 volts. Alright, that's it. We'll go ahead and functional test the meter. Alright, the meter passes functional just fine. You can see I've restrapped our generator. We're now putting out 4 divisions, or roughly 8,000 volts peak. Again, this is a 50 microsecond full width half height, and we're going to be applying 5 transients, positive and negative, with each mode of the meter. And again, this is a 2 ohm source impedance. Normally what you'll see if it starts to break down is it won't follow this decay at all. Alright, that's it. That was 8,000 volts. Let me go ahead and functional test it. Looks like the BM839 survived that test just fine. That was 8 kV. I've restrapped our generator for 10,000 volts. Again, we'll do 5 transients each mode of the meter. You see, we're basically 5 transients up. Okay, that was 10,000 volts. Before we functional test this meter, this is a spark plug, and I'm just going to connect this up at 10,000 volts. That's probably enough to arc across this. Alright, let's give it a shot. Oh yeah, no problem. You can see not a whole lot of energy. Again, we don't need it. We're not trying to do a safety test. Alright, so I've gone ahead and functional tested the BM839. It still seems fine. So that was 10,000 volts. What I've done is I've restrapped the generator. And we can see on our LaCroix scope, this is 2,000 volts per division. We're 6 divisions up, or 12,000 volts. And this is currently at 10 microseconds per division, so there's 10, 20, 30, 40, about 50 microseconds full with half height. I ran the BM235 at this level, and it didn't have any trouble with it. I think that's the only Brymen I've ran up this high, other than the BM869S, which of course failed at 13,000. But that was with a 100 microsecond full width half height. Okay, so this is going to be 12,000 volts, 50 microsecond full width half height, 2 ohm source impedance. Again, we'll do 5 transients, positive and negative. If it passes this test, we'll stop here. It's the last transient. That's it. Just have a quick look. Alright, this should be roughly 70 volts. That's fine. It should be 5. This should be 2.5. That's fine. This should be 2.5. That's fine. Oh. Looks like we've damaged the resistance measurement. You can see 1.2K. Yep, capacitance is damaged. Let's try diode check. Yep, that's damaged. Let's see if the millivolts work. So this should be roughly 118. That's low. Let's try the temperature test. Again, this should be 500, and that is low. So the meter is somewhat functional, but we've definitely damaged it. Still, that's 13,000 volts with a 50 microsecond full width half height and a 2 ohm source impedance. So that was a pretty big hit. Let's go ahead and take the meter apart and we'll see if we can figure out what went wrong with it. can see these huge pins they've got down inside there. So these four have to be all unsoldered, and then we remove the screws for the switch, and hopefully she just slides right apart. So while we have this apart, let's have a look at the contacts. These are definitely dry, just like the other Brymen meters that I've looked at. The wiper contacts look to be identical as well. Alright, so this is our input jack here. You can see this ties to this common point with the two high voltage resistors. This one is in series with this one, and then this one goes back to this PTC here, which goes over to this MOV, and then this one goes up to this PTC, which goes to this MOV. This side of this MOV goes down to this common point as well, and then this MOV returns those two MOVs back to ground. So again, this is a fairly common technique that I've seen. Nice thing about this is where these two PTCs feed into the switches, it looks like everything goes to these diodes up here, and it looks like these two right here might be leaking. I'm just going to go ahead and remove those two. Doesn't look like they're completely dead, but boy, they sure do seem to be leaking. Let me have a look and see if we can figure out what part these are. Alright, these are our two suspect transistors. They're marked RIP, which I believe is a 2N2222. Alright. Here's our two new transistors. Alright, let's do a basic functional check of it. It should be 70 volts. And this should be 65. This should be 5. Should be roughly 2.5. Should be 2.5, and this should be 2.5, both at 60 hertz. Should be 30 hertz. Let's try it in the millivolt range, so it should be 118. Let's try a 10 meg. Let's try a 1 meg. This will be 100K. 10K. 100 ohm. Continuity test. This is a 100 mega ohm, so it should be 10 nanosiemens. Looks good. It's a giga ohm, this should be 1 nanosiemen. Looks good. Diode check mode, so there's a short. And here's a single diode and 2 diodes. This will be a 1 nanofarad capacitor. It's a 0.1. And let's just try temp. Again, this should be roughly 500 degrees. Looks like it varies just fine. Let's just try the microamp range. so this should be 100 microamps, and 10, and 1, and 100 nanoamps. Jack test works. Let's try it this way. Yep, that seems fine. So yeah, it looks like the only thing that we damaged were these two transistors. Again, these are a common 2222 part, or at least they appear to be. So I think we're good to go. We'll continue on with the testing. Next, I'd like to run the 50,000 cycle life test on the rotary switch. So you can see I've attached a couple of test points. I've got that connected to this cable here. We'll go ahead and plug this into the BM839S, and we'll just measure contact resistance. So you can see roughly 0.55 ohms. With the meter off, it's reading roughly 7 meg. Again, the batteries have been removed from this meter. And again, we'll just be using our little M-drive stepper motor. And it looks like it's pretty much up to speed now. Alright, so this is going to take about 60 hours again. The meter now has about 10,000 cycles on it. The meter finished cycling sometime today. Unfortunately, I wasn't around to see the end of it. And the software is smart enough to turn off the power once it's finished cycling. You can see this is kind of how I wired it in. It's actually going through the battery cover, just like so. This white is just the rubber again off of the two fingers. So originally I was going to power this thing up like the BM839S, but I've forgotten I'd unsoldered all these wires, and rather than to have the wear and tear on the circuit board, I thought we might as well just have a look at it. Again, the switch itself, I mean, it feels the same as it did. I don't see any kind of contaminants. You know, looking down inside, it looks fairly clean. Again, just a little bit of rubbing on the edge. Wow, this looks real nice. I'm not really seeing any signs of wear in this at all. Even the contacts look really good. I've never had this bottom assembly apart, so this will be the first time that we're looking at this. The reason I marked all this is because the BM839S, there's definitely a polarity to it, so you have to be very careful that you get it reassembled correctly. Wow. Again, it looks really good. Boy, look at the circuit board. It looks really nice. Let's get the microscope out and we'll have a look at this thing. Alright, I thought this time what we could do is just start by looking at the contacts. You may remember when I ran that BM839S, we actually cracked one of these. So it'll be interesting to see how these look. There's definitely some wear. There's some debris. And again, all in all, it looks pretty good. Let's just have a look at that debris again. Yeah, these two right here, these seem to be by far the worst. Let's just take a closer look at that. And a little bit of build up there. You know, I think the reason that you're not seeing it on these is just because they're worn that much more. There's just no area for them to collect. Although you don't really see a whole lot on this one. Let's have a look at the other side. But all in all, they look pretty good, and I don't see any cracking. So whatever happened with our BM839S, I'm not seeing that repeat with this BM839. Again, the one that we cracked was a smaller one like these two. But yeah, there's no signs of any fractures on any of these. Looks pretty good. Again, just kind of eyeballing it, they didn't look too bad. But here, yeah, we can see there's quite a bit of debris buildup. Yeah, a lot of little specks. But the pads themselves look pretty good. You can see on the edge of a few of these, maybe this one right here. Again, a lot of debris in the center. And you can see how it's eroded the edges. This is looking at the main circuit board. Again, quite a bit of debris. You can see how it's just kind of worn away at the solder mask. There's some big chunks. What that red is. Huh. It's kind of odd looking. It's not even where the wiper contact rides. You can see we're quite a ways away from it. Again, a lot of debris. Tell you what, I think what I'm going to do is go ahead and flush this with some Pro Clean again. And you can see a fair amount of debris. That's the magic marker. And there might be some hints of copper. Yeah, it looks like a little bit of copper right in the center. See how the light's kind of reflecting off of it? But again, not too bad. And this is looking at the mezzanine board after cleaning. That looks really good. Oh, there's one of our cuts. And you notice that that is actually made that way. I was kind of wondering, you can see right along these edges here. You can see how they have these little channels cut into the pad. These look really nice. One thing I'm not seeing with this board that I saw with the BM839S is in between the pads, I'm not seeing a real deep groove getting cut into these. There's just a little bit of wear along the edge, but that's really about it. If you look at this area right here, I mean, that's definitely copper coming through. Let's try rotating the board a little bit. That'll show up a little better. Yeah, right in the center of the screen. This definitely looks like copper coming through. It looks like it's just towards the one side of that pad. Let's look at the other board. So that little red dot again. Just see if we look at that from a different angle. And again, I just don't know what that is. Maybe a defect in the circuit board. Oh boy, the rest of the board itself looks really good. Even on the edge of some of these, it just doesn't look that bad. So our detent spring. Oops. You can see is no signs of any fracture in any of these springs. It looks really good. But again, this does not appear to be a filled plastic. And again, this is after cleaning the circuit board. Looks a little different when you pull it out from under the microscope. And again, this is our little mezzanine board. Looks really good. I think what I'd like to do next is go ahead and reassemble the meter, and we'll power it up and see if it still works. You know, so far I've been very impressed with the Brymen products I've looked at. They've all been very robust, and they're fairly inexpensive compared to most meters that would have this same level of quality. So I've been real happy with what I've seen. Again, that BM839S is by far my favorite meter out of the ones I've looked at. Alright, let's go ahead and reattach everything. There you go. Give this thing a little bit of cleaning. Never did a real good job of this after I changed out those two transistors. Let's get some of this rubber dust out of the center. It looks okay. Again, this is with a short. Looks real good. This is with a 1 ohm. Dead on. Here's with 10 megs. Continuity test. Let's just try it in conductance. So this will be 100 mega ohms. Again, this should read 10 nanosiemens. This is with a 1 giga ohm resistor. Again, this should be 1 nanosiemen. Looks real good. Let's try capacitance mode. So this will be a 1 nanofarad capacitor. Dead on. And a 0.1. Looks good. Let's just try diode check. That looks fine. In the millivolt range. Again, this should be roughly 118. 60 hertz. It looks good. Let's just try temperature. Again, this should be roughly 500 degrees Celsius. And room temp and a little over 1,000. Looks fine. Let's try the microamp range. Should be 100 microamps. 10 microamps. 1 microamp. And this will be 100 nanoamps. Looks fine. Oh, yeah, let's give that a try. Yep, so it picks up that lead fine. Yep, and same thing here. Yep, so that all works. Again, this will be 100 microamps. So 0.1 milliamps, that looks fine. Let's just try it in the amps jack. This should be about 40 milliamps. Looks fine. Let's try the DC volts mode. Again, this should be 5 volts. Dead on the money. This should be roughly 60 volts. That looks fine. Let's try it in AC volt mode. Should be roughly 70. Looks good. And this should be roughly 2.5 at 60 hertz. Looks good. This is DC coupled. So it's switching between 0 and 5 volts, 2.5 volts again. That looks fine. This will be at 30 hertz. Yeah, so it looks like the meter's just fine. I'll go ahead and button it up the rest of the way. So let's have a look at the data that we've collected for the meters. And here we can see the green trace is the Brymen BM839. And again, D means that it's a dry contact meter or there was no lubrication. N means it's a brand new meter. So this is looking at the mean or the average data. Let's go ahead and look at the raw data. Again, this is basically what the meter returns as it's reading the switch contact resistance. So you can see it's quite a bit more noisy. That's what the filter is doing for us. And again, this is looking from 0 to 1000 ohms in the vertical axes. And then across the horizontal axis is the number of cycles. Let's deselect a few of these meters. So what we have left is the Agilent U1231A. If we go ahead and deselect him, this is the 2 Brymen meters and the fluke meter. So you can see these are way down in the muck compared to the rest of the meters. Let's go ahead and look at this in 3 dimensions. So again, this is looking at the BM839. And you can see the vertical axis is 0 to 1.3 ohms. We have one little peak up here, just towards the very end of the test where it reached that high. Looks like there's another spike right out here early on. All in all, the meter's fairly quiet. This was our baseline meter. Here's our key site. Here's the Kassun test. Again, this is the fluke. Here's our EM129. This is our Suntech meter, and again, this is flat because I aborted the test, and that was because the meter basically opened up. So this is the Brymen BM869S. And you can see it compared with the BM839. They're similar. I would say the BM869 is definitely a little cleaner. Let's go back and look at the multi-plot, and let's just zoom into this thing a little bit. And again, let's go ahead and deselect some of these. So again, this white trace is our key site meter. The blue trace is the Brymen BM869S. And the green is the BM839. And then this gold trace at the very bottom is the Fluke 17B Plus. Let's go ahead and disable the Agilent meter, and we'll disable the Fluke. So this is looking at just the two Brymen meters. And you can see they both start out very similar. I would say again, the BM839S, right here, it's already getting a little noisy. And it kind of drifts up a little bit. You can see where the BM869S also had that kind of an upward trend. Then it sort of snaps back. And you can see once we get out to about 1300 cycles, the BM869S quiets right down. There's a little bit of a spike out here, but again, it's nothing compared with the 839. Let's go ahead and look at the log data. And again, for this graph, both the vertical and the horizontal are in log. The vertical is the number of cycles, and the horizontal is the resistance. It's interesting, you can see the 839 again is in blue, and the yellow is the 869S. And you can see there's a crossover point at roughly 0.2 ohms, and this happens at roughly 5,000 cycles in. Looks like after that the BM839S is doing a better job than the BM869S. Of course, they both eventually reach roughly 1 ohm. We can display this as an average as well, so if we come over the main screen, we'll select the mean, and now we can display the log, and you can see that changes the profile slightly. So yeah, I would say the BM869S performed a little bit better in this test than what the BM839 did. Of course, when we ran the BM869S, we fractured one of the wiper contacts. And again, I had contacted Brymen about that, and they have never seen that before. But again, I do run 20,000 more cycles than what they do. But that does seem to line up with what we saw with the BM839. Again, we didn't see any fractures in the contacts on that meter. But it does look like Brymen is doing a very good job with their switch design. Certainly better than most of the ones we've looked at. The only one that we've looked at that's better than the Brymens is that Fluke 17B Plus. It's not a whole lot of data yet, but you can definitely see that, you know, there is a difference in the quality of the meters. I think we're going to go ahead and wrap up this video. Again, the BM839S is fully functional right now. You can see the switch works just fine. Again, this is after the 50,000 cycles. You can hear basically sounds the same as the BM869S. Definitely needed a good cleaning after that, but other than that, no real problems. I have a few comments about the meter. While it is very robust, there's a few things I don't like. One of them is that it's got this problem where it reads 2 times the frequency when I put in the high voltage. I still don't know what's going on with that. That was totally unexpected. You know, this particular meter, they said, was about 80% of this Brymen BM869S. And, you know, when I look at the features between these two, there's a few reasons I really like this BM869S. First of all, it has 2 temperature inputs. So you can actually connect 2 different thermocouples to this meter, and then you can display them both simultaneously. See, T1, T2, or you can run split display with it. Another thing with this meter is it supports the AC plus DC mode, and again, that's something I use fairly often. Again, with the BM839, it's normally only a 6,000 count meter, where this is a 50,000 count meter. The only thing about the BM869S is it's a little more accurate at reading lower resistances. They did have this special mode that you could put it into to try to compensate for errors of the meter and the leads. It's similar to a REL, but it's a special mode, and it did improve it, but it's still not as good as what this BM869. So for me personally, I would rather spend the money and get this BM869S over this one. The cost savings just aren't significant enough that would drive me to buy this meter. Again, the meter itself was pretty good. It looks like there's only the one problem that I came across with it. It's just it doesn't have the features that this one does. Well, I think that's going to be it for this video. Hopefully you found it useful, or if not, maybe entertaining. Again, I'd like to thank Brymen for supplying all these meters. Again, they sent those meters to me knowing what I was going to do to them. Also looks like we picked up quite a few new followers. I don't know what you're doing here, but glad to have you on board. Well, until the next test, later.